All right, today we're going to try and crack one of the biggest, most complicated enigmas in all of modern medicine, and that is inflammation.
It's true. Your body is telling a story. It's constantly sending out these little signals to heal, to defend itself, to rebuild. But what happens when those signals get crossed? When that conversation breaks down? Well, that's where we get into the world of inflammation. And that's where we start running into some of medicine's biggest, most stubborn mysteries. So first things first, let's meet our main character. And trust me, it's a character with a serious split personality. Inflammation itself. Think about it like this. On a good day, inflammation is your body's personal superhero. It's the first responder rushing to the scene of an injury or an infection, ready to start the healing. But when that system goes haywire, when it just refuses to stand down and stays on high alert, that's when our hero becomes the villain. It becomes a driving force behind so many of the chronic diseases that are so tough to deal with.
So, today, we're not just going to talk about what we know. Nah, we're going to play detective. We are opening up the cold case files on inflammation. We're going to look at the gaps, the things that make scientists scratch their heads, the real, genuine mysteries that are still out there.
All right, so where does any good detective start? With the big questions, right? Let's dive into the areas where the clues they don't add up yet. These are the great unknowns. Okay, let's start with a big one. You've heard about it, I've heard about it, it is everywhere. Intermittent fasting. It gets pitched as this magic bullet for everything from losing weight to fighting off disease. But what's the real story? What does the science actually say when it comes to inflammation?
And this is where our detective work kind of hits a brick wall. For all the hype, when you actually pull open the scientific file drawers on how fasting affects these specific conditions, a lot of them are pretty empty. We just don't have those really solid long-term studies we need to say for sure what's going on. For so many of these things, the hard evidence, it just isn't there yet.
Or how about this? A classic case of mistaken identity. You've got two conditions. One is an autoimmune disease in kids, juvenile idiopathic arthritis. The other is a reaction to an infection somewhere else in the body. On the surface, they can look almost exactly the same. Same inflammation, same symptoms. But the cause is totally different. And here's the kicker. We don't have a good fingerprint, a specific antibody, to easily tell them apart right at the beginning. And that makes getting the right diagnosis fast incredibly tough. And, it just keeps getting trickier. The case gets even more complicated when you start throwing in all these other variables that just muddy the waters and make a clean investigation, almost impossible. I mean, take something that seems simple like hormonal status. A premenopausal woman and a postmenopausal woman have totally different biological and metabolic stuff going on. So, something like intermittent fasting, it's probably not going to affect them in the same way. The impact could be wildly different. It just goes to show, one size definitely does not fit all. We can't have just one simple answer. And then, there's maybe the biggest complicating factor of all, just getting older. When we're young, our body's cleanup crews, these cellular repair systems, are amazing. They're on top of everything. But as we age, they they slow down. That means junk, these abnormal molecules, starts to pile up. And what does that do? It triggers this low-grade, chronic inflammation throughout the whole body. Some scientists even call it inflammaging, and it's a huge suspect in a lot of age-related diseases.
Sometimes all this complexity just boils over into total chaos. The perfect example is sepsis. With sepsis, the immune system doesn't just go into overdrive. No, it does that and shuts down at the exact same time. You can have one part of the body literally on fire with inflammation, while another part's defenses are completely offline. It's this perfect storm, and it's different for every single patient, which makes it an absolute nightmare to treat.
Okay, so with all of this mess, all these complications, how on earth do scientists even start to untangle it? How are they actually trying to crack this code? Let's take a look at a real-world example that really brings this challenge to life. Meet cisplatin. It's a powerful chemo drug, and for a lot of cancer patients, it is an absolute lifesaver. It's a superhero at destroying tumor cells. But, like a lot of superheroes, this one has a dark side. That same powerful attack that kills cancer cells also creates a ton of friendly fire. It leads to this thing called oxidative stress, which then triggers massive inflammation and causes serious collateral damage, especially to the kidneys.
And that right there, that is the million-dollar question for researchers. How do we get the good without the bad? How do you keep the life-saving power of the drug, but get rid of, or at least dial way back on, the devastating side effects? That's the puzzle they're trying to piece together every single day.
And solving that puzzle usually follows a pretty clear path. It's like a scientific hunt. Step 1, you got to find a reliable marker, like a flare that signals the disease is here. Step 2, you have to figure out the mechanism. How does this thing actually work? And finally, step 3, once you know all that, you can develop smart, targeted therapies that go right for the root cause. Each step is built on the one before it.
Which brings us to our final clue. And honestly, it might be the most important one. Because this whole investigation, it's not just happening in some far-off lab. It's happening inside every single one of us right now. So, one of the most important tools the detectives have is something called a biomarker. The best way to think of it is like a biological fingerprint. It's some measurable signal in your body that tells a story. It can tell scientists if a disease is there, if it's getting worse, or even if a treatment is doing its job. Finding the right biomarker is like finding that one critical clue at the crime scene that cracks the whole case open. And the ultimate goal, the reason they're looking for these clues, it's to understand something called pathogenesis. That's the whole story, the entire sequence of events of how a disease gets started and develops. So if the biomarker is the fingerprint, then figuring out the pathogenesis, well, that's like discovering the motive. It's the why behind the whole crime.
And again, this isn't just some abstract scientific idea. From our gut to our brain, from our joints to our heart, this entire investigation is taking place inside of you. All of these huge, unanswered questions are literally stories unfolding inside our own bodies every single day.
So really, your body holds the clues to some of medicine's biggest mysteries. It's the scene of the crime, the book of secrets, all rolled into one. And that just leaves one final, thrilling question. What secrets is it going to reveal next?